Hello everyone and welcome to lecture 16. As you can see, today's topic is least square method. This is quite a fascinating topic, but at the same time this might seem a little challenging to some of you, so I kind of need you to focus in this one. Alright, so let's start. But before we actually go into the topic of least square itself, I want to review a couple of things first. And the first one of those is the concept of orthogonal complement. So the definition kind of goes like this. If we have a vector space V inside the space S, so V is a subspace of S, then the orthogonal complement of V is going to be the set of all those vectors which are still in S. So all those vectors of S such that V dot W is equal to 0. So the set of all such vectors W, and as you can see, V dot W is equal to 0, which just means that W is perpendicular to V, because the dot product is 0. The dot product is 0 only when the two vectors are perpendicular. So what, let's just show it like this. We have a vector space S, alright. So our V is a subspace of this space, and the orthogonal complement of this vector space is going to be W, which is a set of all such vectors that if you take any vector from V, all the vectors of W is going to be perpendicular to all the vectors of V. So the orthogonal complement is just the set of all such vectors. All right. Okay. And the next thing we need to remember, oh, there is something else. The dimension of the vector space V and the dimension of its orthogonal complement, this is also a vector space, by the way. So the dimension of this space and the dimension of this space, together they will be equal to the dimension of the universal space. So yeah, all right, so that's done. The second thing I need you to remember is that the column space of a matrix, if you remember from week 7, there are 4 fundamental subspaces: the column space, the row space, the null space, and the left null space, which is basically the null space of the transpose matrix. All right, so the column space of a matrix and the left null space of that same matrix are orthogonal complements of each other. Okay, so if we have the column space of this matrix, this is the sign of orthogonal complement. So the orthogonal complement is going to be the left null space. But we also know the left null space of a matrix is just the null space of the transpose matrix. So what I'm saying is the column space of a matrix is going to be perpendicular to the null space of its transpose matrix. If you don't remember where it is from, this is a snapshot of your week 7 lecture note. So here it is quite beautifully explained why we have the row space and the null space are orthogonal complements of each other, and what we are concerned about right now, the column space and the left null space are orthogonal complements of each other. So if you forgot or if you don't know what I'm talking about, just go back to week 7 and take a look at this. All right. So these two concepts, the concept of orthogonal complement and the information that the column space and the left null space matrix are orthogonal complements of each other, these two information is going to be important in this video. So I'm just getting done with it before I move on to the original topic. So we are done with it. Now let's move on to our actual topic. Let's say we have a system of linear equation. As you can see here, very familiar 3x3 matrix, a three-dimensional vector, solution vector, which is equal to another three-dimensional vector. All right, so to find the solution of this matrix, what we do, we perform row reduction, right? Sorry, we perform row reduction. So let's convert this one to the reduced to echelon form. I'm not going to show you the whole process. It's very old. You know how to do it by now. But the interesting thing is this system is inconsistent, because as you can see, we have a 0 row right here, of which multiplied by this vector is just going to give me 0 into x plus 0 into y plus 0 into z, which should be 0, but on the right hand side I can see that this is equal to 1. which is clearly a contradiction. So this is not a consistent system. Okay, so we cannot actually solve this, right? Because there is no solution. There is no solution to this system. But what if I still wanted to solve it? Well, as you can clearly see, I cannot really find an exact solution because the exact solution does not exist. But I can get close, right? I can find a solution that is not completely correct, but that is my best possible solution. It can happen, right? So I'll show you what I mean. Okay, so as you can see here, we are showing you a three-dimensional space. This is the XY plane. So right now, I'm going to draw my three column vectors. The first one was 2, 1, 1, right? So this is the point, let's just say 2, 1, 1. This is the first column. This is my second column. And this is going to be the third column. All right. So the column space is going to be the span of these vectors. So if I span these three vectors, I'm going to get the column space, which happens to be this thing. All right. So this plane, as you can see, the three columns are not actually linearly independent. Well, if they were linearly independent, I would actually find the solution for any matrix, any vector in this three-dimensional space. So the contradiction wouldn't even appear to begin with. But these three vectors are not linearly independent. So two of them are linearly independent of each other, and the third one is dependent on the other two. So if I span them, I'm going to get a plane of dimension 2, right? So what about the vector of our right-hand side? So the vector of our right-hand side is this one. And as you can very clearly see, this vector is not inside the column space. And that is exactly why we could not find a solution, because the vector does not reside inside our column space. So the columns cannot get to this point right here, this point right here, the point D. Okay, so that's fine. But if I want to find the closest vector that is inside the column space, this plane right here, a vector which is inside this plane, which is closest to this vector A, it should be B in our example. So the right hand side vector, the purple one, is this purple or pink? Anyway, not important. So this colorful vector, I want to get as close as possible to that vector, but you know, we cannot go beyond the column space. This plane is what I can, this plane is all I can go to. So the closest vector of this right hand side vector, this purple one, is going to be the projection of this vector onto this plane, which is going to be, I think, this one. So this is the projection. All right, so the projection of the purple vector is the pink vector, the projection onto this plane. I can reach the pink vector because that pink vector, as you can see, is inside the column space. And I think you know, I don't have to explain it, that this is the closest vector you can get to. The closest vector to this vector inside this column space is going to be this pink one. And we could not reach, this is the part of the actual vector that we could not reach. So this is the projection, and this is the part that is left after we took the projection. So this is going to be perpendicular to our plane, right? So as you can see, this is a perpendicular vector to our plane. So as we are done with our projection classes, I think all of this should make sense to you, what I'm saying. So if I want to summarize this again quickly, we have the black vectors are my column vectors. So by spanning them, I got the blue plane. But my right-hand side vector is the purple vector, which is not inside my column space. And that is why I cannot reach there. So I cannot find any solution. But the closest solution I can find, which I can actually reach, is this pink vector here, which is actually in fact inside the column space, and this vector is the closest vector of my actual right hand side vector, because the pink vector is actually the projection of the actual vector, and we know if I take a projection of a vector on a plane, that is going to be the vector at the shortest distance, and this orange vector is that distance. And from the laws of projection, we know that this orange vector is going to be perpendicular to my plane. All right, because everything other than the perpendicular portion is inside. I have taken that in the pink portion. Okay, so once we are done with that, I hope you understood that. Let's go back to our blackboard and do the calculations and derive the formulas. All right. So we are back at our blackboard, and this is the figure that we just saw. I'm going to give you the names again. The black vectors are the column vectors. The blue space, the blue plane is my column space. The B vector, purple vector, is my right hand side vector. And the B hat vector is the projection of the vector B onto the column space. So if I subtract the projection from the vector, what I'm left with is the perpendicular vector, that is B minus B hat. Okay, so Ax equal to B has no solution. I cannot find an X for which I can go to B, all right, because B is not in the column space. But Ax equal to B hat has solutions. It can be one solution or it can be infinitely many solutions. And I can say that because B hat actually is in fact inside my column space. So of course I can find an X for which I can solve this. So there is at least one solution. There can also be infinitely many solutions. In this case, we will get infinitely many solutions because we have linear dependencies. We have three vectors, three column vectors in a two-dimensional plane. Anyway, so moving on, B minus B hat is perpendicular to the column space of A, right? And we know that anything that is perpendicular to the column space of A must be a member of the orthogonal complement. This is exactly why I went through the definitions at the start of the video, because this is important. We know that the orthogonal complement of a space is anything and everything that is perpendicular to this, right? So as this vector, this orange vector here, is perpendicular to the blue plane, this orange vector must be inside the orthogonal complement of the blue plane, and the blue plane is just the column space. And we know the column space of a matrix has the orthogonal complement, which is the left null space, right? So B minus B prime is in the left null space of A. And we also know that the left null space is just the null space of A transpose. So we have that B minus B prime, B hat, is a member of the null space of A transpose, which follows, which gives us that this equation will yield 0, because as B minus B prime, B hat is a solution, is a member of the null space of this matrix. So from definition, we can say that AT into this matrix is going to be 0, because this is inside the null space. So if I break this down, I get, before breaking it down, let's just write B hat. We know that Ax equal to B hat. The X is this X, because I cannot find this X. I can find an X for B hat, so that is what I'm trying to do. Because B hat is my closest vector, so I'm trying to find the closest solution. So I can replace B hat with Ax from this, then we break it up. We get ATB minus ATAX, just multiplication. And then I take this portion on the other side, and this is the equation I'm left with. And this equation will have a solution, because I just explained why this is going to have a solution. So I can find my X from this equation. I could not find it from this equation because this does not exist. So I'm trying to find this one, and I'm trying to find this one using this. All right. So let's just look at, before that, this B minus B hat is the part that we left behind. All right, because B hat is not exactly B. I could not find solution for B, so I am just trying to cheat and trying to find the best possible answer, which is b hat, but they are not equal. So the whatever that is left, b minus b hat, this distance is the error, all right? The part that I could not calculate, the part that I am just ignoring for the sake of finding a solution. All right, so let's see. This is my system that we saw. I know we don't have a solution for this. So what I'm going to do, I'm going to multiply A transpose, which is the transpose matrix of this one, on either side. And if I do the multiplication, I will end up with this matrix. I'm just showing you again. So this was my system after multiplying A transpose on both sides. And now I'm going to do this multiplication and this multiplication. So my system looks like this. And now I can find the value of x from this, because this is going to have a solution. So if I again perform the row reduction process, after elimination, I'll find the reduced row echelon form, which is this. This is the reduced row echelon form. And as you can see, I don't have an inconsistency anymore. All right. I have a free variable, as I said, so I'm going to get infinitely many solutions for x, which will give me the projection matrix, projected vector, sorry. So as you can see, I can find many solutions that will give me the closest possible vector, which is b hat. So any solution of this system is the best approximate solution of my original system, which is this one. Not this one, sorry. Not this one still. This one. All right, so this is any solution I find of the modified system is the best approximation of this system. This system has no solution, but I just found out the best possible solution I can get. All right, so moving on again. Now our topic is almost over. I'm just going to show you why this is very important. So let's see. This is an example of a dataset, very small dataset. So what we're trying to do is let's say you are trying to build a machine learning program which will provide you with an estimate of what should be the price of a house. And after much analysis, you find out that the price of a house depends on mainly 4 things. The area of the house in square feet, how many bedrooms it has, how many bathrooms it has, and the neighborhood it is in. So there is a numerical measurement of the goodness of the neighborhood. All right, so we call these things the features. We have 4 features. So your program actually tries to estimate the price of a house based on 4 features. And the equation that we are going to use is this one. So basically each feature has a certain weight. I know the area of the house is important, but I don't know how important it is. Similarly, I know the number of bedrooms is important, but I don't really know exactly how important it is in measuring the price. So I'm going to get that weight, this weight 1, weight 2, weight 3. Weight 3 is the weight of the 3rd feature and so on. I'm trying to get the values of this weight from a data set. We are going to collect the data of many houses and try to determine the values of these features, the weights of the features from this, right? So this is the data of 5 houses. We can say that if we have 800 square feet and 2 bedrooms and 2 bathrooms and the neighborhood rating is 3, the price is $190,000 something. This is $330,000, basically 330K. So yeah, 1300 square feet, 3 bedrooms, 3 bathrooms, but this one is in a really good neighborhood, and that is why the price of this one is much higher than any of these. All right, so this is your data, right? So if we convert this in a matrix, as you can see, this is a 1 2 3 4 5 by 4 matrix. So this is actually convertible in a system of linear equation. A 5 by 4 matrix, we have got 4 columns, so 4 features, 4 variables, and our right hand side. So by solving this, we can find out the values of this one, right, from our data set. But in real life scenarios, almost every single time you will not get a solution. You will not get a perfect solution that matches every equation, every scenario, every case of the house. So this system, without even judging, I can pretty much guarantee that this system does not have a solution. But what you can do is you can find the closest solution. You can find the best approximation, and for that you will need the least square method. So if this is the matrix A, this matrix is going to be, you are going to multiply this with A transpose, multiply this with A transpose. You're going to get a new system, solve that. That is going to be solvable as we just showed, and that solution is going to be the values of your weights. So you see, not a very difficult process, but you can make quite useful things with it, right? So yeah, that's it. I kind of forgot about one important thing, and that is when you have an inconsistent system like this, when you have something like this, you do not do row operations. Because when you do row operations, before you multiply A transpose with A, if you, for example, if you add row 1 with row 2, we do that all the time in consistent systems. And that doesn't cause a problem because we are going to get the exact solution every time. But if you do row operations before this multiplication, you might change the answer of the least square method, because this is a data point, all right? 802.23 is $190K. This is a data point, this is another data point. If you add this, which is a valid row operation, you are going to get a house of 2000 square feet, which has 5 bedrooms apparently, 5 bathrooms, and the neighborhood rating is apparently 5. And the price of that house is going to be $415K. But that data point, why this is going to be that row? If you add this 5, 5, 5, this is probably going to be 405, right? 405K. This data does not exist. You just invented it. We don't have a house that has this data. So judging by these two equations, yes, you can do that. But as this is an inconsistent system and we are just trying to find the best approximation based on some data, if you do row operations, you are going to create false data, which is not a good idea to do. And also, if you look at our figure, this one, you know, row operations change the column space, right? So if you do row operations before you do the multiplication, which converts it into a solvable system, you are just changing the columns, and that means the blue plane is going to change, the column space is going to change, so the projection is going to change. So you are basically changing the projection. So doing row operation before you do the multiplication with a transpose for finding the solution will change the answer to your least square problem. You just have to keep that in mind. Alright, so that's it for now. We are going to have a small second part of this lecture. Until then, goodbye.